everybody. So welcome back to Geology 3104C, Paleontology and Stratigraphy at the University of South Florida. This is Sarah Sheffield. So today's lecture is going to be on biostratigraphy. We've already covered what stratigraphy means, right? Studying rock layers. So today we're going to be specifically focusing on biostratigraphy. And if the picture wasn't enough, bio of course means life. So we're going to be studying how fossils can tell us about stratigraphic correlations, finding out the ages of rocks and things like that. So this drawing is a famous one from William Smith, who is essentially, how would you put this? He is the founder of biostratigraphy, really. Okay? All right, so quick primer on fossil grammar, because this is a paleo class, of course. You're going to need to learn a little bit about how we write about fossils. And so I will be modeling this for you, of course, throughout the class, but I will be expecting you to feel more comfortable using this type of grammar as well. So first, all fossil genus and species names are italicized, always. All right, just like Tyrannosaurus in the next line is capitalized or is italicized, Rex is also italicized. Any other, so kingdom, phylum, class, order, and family, not italicized, just genus and species. That's how you recognize it when it's written. Genus name is always capitalized. The species name is not. So Tyrannosaurus rex, the T is capitalized, the R is not. You can abbreviate by writing T-Rex, which you see a lot, obviously, but technically you can only do that if you write Tyrannosaurus at some point before it. You know how like you need to introduce the acronym before you use it in proper writing? It's the same type of thing. The reason for that is there's a whole lot of species names that are the exact same. So if you write T-Rex, there are chances somewhere that there is another genus with a T name and a Rex species. So we always have to be careful to be specific. So again, practice these good habits. Anytime you type up about fossils, this is how you do it. Obviously, you don't write in italics with a pencil, but capitalization and things like that is always important. All right. So biostratigraphy, the branch of stratigraphy concerned with using fossils and dating rock formations with them. So we're going to tell you a little bit about William Smith because it's a cool story. All right, so this is William Smith, very joyous dude, as you can very clearly see from the photo. He worked as a surveyor for the Somerset Coal Canal Company. However, he was not well off. We'll say that. He didn't have a whole lot of expendable income. However, he was fascinated by fossils in the rock, and specifically, he was really fascinated by how specific fossils showed up in specific places. So he noticed throughout when he was traveling the country for work that certain fossils only appeared with other fossils, so assemblages. All right, so certain shells only appeared with other shells, and vertebrates only appeared in certain places, things like that. So this is one of his quotes from his writings. Fossils have long been studied as great curiosities, collected with great pains, treasured with great care, because they are pretty. And this has been done by thousands who have never paid the least regard to that wonderful order and regularity with which nature has disposed of these singular productions and assigned to each class its particular stratum. So he's really starting to see that there is an order to the fossil record. It's not just chaos, okay? So this is an important note because for a long time, a lot of the ideas about what fossils were and how they came to be where they are has to deal with the catastrophic flood. All right, so a lot of people at this time are still pretty sure that the reason we've got fossils is because of a catastrophic flood in our recent past. So we're starting to get past this movement to see that maybe the fossil record is something that extends far beyond that. And it's actually, fairly predictable. It's not just one flood, but many events that have led up to this. So this is an important movement in scientific understanding. So here is the map that he made. All right, so the geologic table based on what fossils are present. He has color-coded it, that's what this is, and there's names of the different rocks that there are. So he made the first known, and that's really important, the first known large-scale geological map, which is great. Unfortunately, he was so obsessed with making this map, he ended up not paying a lot of things that he needed to, and he was sent to prison for his financial debts for a time. So that's a little bit boo. All right. So as he said himself, my income is as yet not anywise improved by what has been done. So there you go. So this is the map that he made of England and Wales and Scotland. All right. This is the modern day map. You could say, wow, right? Look at the similarities between these two. Now, he made this just with the fossils, which is incredible. But you'll notice, obviously, there's a lot more detail here on the right side of the map. This is a modern geologic map of the UK. All right. And there's, again, a lot more detail, and there's a lot more filled in. The reason is a great geologic map can't just be based on fossils. We have to fill it in with other types of stratigraphy as well. But this is an incredible job that was, the first attempt. So John Phillips' nephew took up what William Smith didn't get to, and he defined the first units on the geologic time scale: Paleozoic, Mesozoic, and Cenozoic, meaning ancient, middle, and recent life, respectively. We still use those names today. As I'm sure you're aware, you're probably familiar with these words already. We still use these names for the Phanerozoic eras. All right, so the Phanerozoic is an eon, and these are the 3 eras within it. So Phillips correctly assumed that these were separated by major extinction events. So he didn't exactly know what was going on, but he was absolutely right, because at each one of these boundaries, we see a huge shift in life, right? The Permo-Triassic extinction marks the boundary between the Paleozoic and the Mesozoic, and it was named because of this huge shift in what was alive. Biostratigraphy, though, can be a lot more precise. It is one of the most reliable ways of correlating different rocks of the same age around the world. So there's a couple things that we need to know. So the first is, what is a biozone? A biozone occurs between the first appearance date and the last appearance date, the FAD and the LAD. When you write about things like this, it's totally okay for you just to say the FAD and the LAD. I'll know what you mean, okay? A biozone is the basic biostratigraphic unit, similar to a lithostratigraphic formation. So a total range biozone is just the entire amount of time between the FAD and the LAD. Now you'll notice I didn't say the total lifespan of this species. I said the first and last appearance date. The reason for that is that we don't always know when the first and last appearance date are. As you can imagine, in paleontology, we don't always know exactly when a fossil went extinct, when was the last surviving member of a species on Earth. We don't know that. We can't say that for sure. Like, when did the last T-Rex finally kick it? We don't know. Sorry, T-Rex, that was incredibly disrespectful. Okay, so we always remember that our total range biozones may change. We might find new evidence, things like that. A concurrent range biozone might be defined by overlapping species ranges. So for example, we can take the time where A, B, and C all lived to get a very specific chunk of time between that. This is a concurrent range biozone. So an assemblage biozone is very similar, where large numbers of zone species overlap. And then a partial range biozone. This can be defined as the start and end of species ranges using a number of different species. So for this particular example, we have a partial range of C species which existed between the LADs of D and C. All right, so we've got D and C as our LADs here, which means that we've got A and B existing within it. We can get a solidly specific chunk of time there. So this is the building blocks of biostratigraphy here. With all of this, it is incredibly useful, and it allows us to do precise correlations, especially if we're using the correct fossils to do this with. Okay, so here, faunal succession uses overlapping fossil ranges. Here we have the ranges of some groups. To read this chart, these are the fossil species still living. These are where they went extinct. All right, this is a trilobite, a clam, a leaf, a T-Rex skull, it looks like, or some theropod dinosaur, another leaf, a starfish, and a brachiopod. All right? So let's use our overlapping fossil ranges. Let's say here is the age of rock unit B. B should have this collection of fossils in it. Excellent. We've got a trilobite. Cool beans. We also have a clamshell. That's making things a little bit more specific. It has to exist between this chunk of time because we've got our trilobite friend and the clam friend between the FAD of the clam and the LAD of the trilobite. All right, so now we also have other fossils existing within that range, so we know it has to hit within this particular time. And the same up here. So that's a pretty useful thing to do. So now the question is, what makes a good zone fossil? Not every fossil you find is going to be great for correlating things. Think about all those times you see first discovered this fossil. As you can see, if it's been first discovered at this point, it's probably not going to be super duper helpful for correlating things globally. So there's some other factors that we need to worry about. So first, these are fossil foraminifera. They're microfossils. They're really cool. They're exceptionally good biostratigraphic markers, and we'll talk about why that is. The first is that the species are rapidly evolving. So if we have species that stay the same or similar to each other for millions of years, think about a ginkgo tree. All right, a ginkgo tree, the fossils have remained almost unchanged from their appearance for 65 to 70 million years. That is not helpful for us in terms of biostratigraphy. I'm not going to use the phrase living fossil, and we'll talk about why that is. A living fossil is not the best term for something that hasn't shown a lot of appearances of changing. Same with sharks or alligators. A lot of people will call them living fossils as well. But there are things that rapidly evolve, and foraminifera, are one of those. So we can see changes happening on thousands of years timescales. They have to be common, right? So a T-Rex skull, not going to be super great. We've only got 9 of those, 8 of those, and they're all in the United States. So that's really going to be unhelpful. Excuse me, they're all North America. They're easily identifiable. All right, so we need to be able to pick out which species is which. And global and facies independent distribution, meaning we can't have something that only exists within a certain type of rock, a very, very specific type of rock, and they have to exist globally. So this is the chart that shows our ideal zone and facies fossils. So we can have fossils that indicate the type of environment something is living in, all right? We could also have something that indicates the age that something is living in. So time and space, environment, and geography. There is an intersection of these 2 points that makes for either an excellent facies fossil or an excellent zone fossil. The shorter amount of time a specific species lived, the better index fossil it is for biostratigraphy-wise, all right? And that's important to talk about. So are dinosaurs good or bad zone fossils? These, of course, are not real dinosaurs. Hopefully you knew that already. But they are not good index fossils. They are not rapidly evolving. Most large animals aren't. They are not common. They are extraordinarily rare comparatively to other organisms. They're not necessarily easily identifiable because a lot of the times we just find chunks of bone. And they don't have a global distribution, and they're not really facies independent. All right. Fish, good or bad? This fish is super duper cool. This is from the Green River Formation in North America. It is gorgeous, some of the best fish fossils you'll ever see. And here is one fish eating another fish while sadly being destroyed and made a beautiful fossil. Really cool. As a side note, you are not supposed to use quarters or nickels or things like that for scale, because if you are not in the United States, you may not know what size that coin is. So are fish good or bad? They're not so great. They're not rapidly evolving. They're not necessarily easily identifiable. They are global, and some of them have a facies independent distribution, and fish fossils aren't uncommon, but still not great. We can do better. Ammonites. So the ammonite is this thing here. That was a joke. Sorry. All right. So, sorry, Gunner. Ammonites, are they good or bad? So ammonites are related to the modern day octopus. In life, it would have had some tentacles and other things sticking out around here. They're super cool looking. They make gorgeous fossils. Ammonites are excellent index fossils. They are rapidly evolving. They are exceedingly common. They have a global facies-independent distribution, and they're easily identifiable to paleontologists. I should always add that caveat. They're identifiable to paleontologists. So these live in the ocean, and they are globally distributed for a very fun reason. This is a scientific concept we'll learn more about later called the bloat and float. I kid you not, the bloat and float. After an ammonite dies, its chamber is filled with gas, which causes it to float, meaning it is distributed across the world, and then eventually they will sink. All right? So they bloat with gas, and then they float along, and then they sink later. So we get global ammonites from very specific chunks of time, which make them excellent index fossils. The more you know. So here is why they're easily identifiable. They have sutures all over their bodies. All right, and the pattern of the suture can tell us a whole lot. For example, goniotitic sutures from the Devonian only really existed from the Devonian to the Permian. Ceratitic sutures from the late Permian to Triassic, and you can see that they're getting more complex through time. These went extinct during the KPG extinction, the Cretaceous-Paleogene extinction, which also took out the non-avian dinosaurs. Plankton, good or bad? Excellent. All right, so they are rapidly evolving. They are common. They're easily identifiable, and they are globally facies-independent distribution. Excellent. Pollen. This is a bee covered in pollen. Super precious, right? Good or bad zone fossil? Excellent. So rapidly evolving, common. I believe all of us in Florida know just how common pollen is, right? Easily identifiable. If you didn't know pollen looks like this under a microscope, it is very identifiable. Every single species that puts out pollen is really, or not every single species, excuse me, but they're very distinct in the fossil record. And they have a global facies-independent distribution. We all wish it wasn't so, springtime allergies, but there you go. Here are the best zone fossils for each time unit. All right, so here are our different groups from forams, those little microfossils, sponges, corals, bryozoans, brachiopods, bivalves, gastropods, nautiloids, ammonoids, belemnites, trilobites, ostracods, crinoids, echinoids, and graptolites. Some are better than others. For example, echinoderms, which are these two groups here, crinoids and echinoids related to the modern starfish, they are crappy index fossils pretty much throughout all of time. Graptolites have a really strong hold on index fossils in the Paleozoic. Trilobites are really, really great throughout a huge chunk of the Paleozoic, though they do go extinct at the Permian extinction. So brachiopods, these have an incredibly good biozone record that stretches throughout almost the entire Paleozoic into some of the Mesozoic, though they are hard hit in the Permo-Triassic extinction. So these are really helpful for us, both on a global scale and a regional scale as well. These are the really common ones that you will focus on. So Cambrian Index fossils, and trilobites are really the Cambrian's index fossils, and they're really good at it. So here are just some examples of some trilobites. They're incredibly easily identifiable, right? They're gorgeous to look at, though that's not part of the criteria. They are globally distributed, they are common, all right, and they are fairly facies independent, meaning we can use these very well. Some Paleozoic index fossils, so excluding the Cambrian for this particular conversation, we have graptolites, which are these things right here. We have conodonts, we'll talk more about conodonts in a little bit. We have brachiopods, we have bryozoans, where are my bryozoan friends? Here they are, corals, and we have some foraminifera here. These are some really strange foraminifera called fusulinids. They kind of look like grains of rice. You will learn more about these types of fossils when we go through each group specifically. Our Mesozoic index fossils, so living at the time of the non-avian dinosaurs, like T-Rex and Velociraptor. All right, we have ammonoids, gastropods, and bivalves. So all of these here belong in the mollusk group, along with octopi, and things like that. So here are our good old friends, the ammonites. You can see those suture patterns. Beautiful. If you remember, These are the super complex suture patterns we saw. So these are ammonitic sutures, which means it is some of the later living ammonites. I'll talk to you real quick about these. This is a rudist bivalve, R-U-D-I-S-T. So kind of like, wow, that bivalve's so rude. I'm kidding. These could be the size of trash cans. Horrifying, right? Cenozoic index fossils. So Cenozoic is the past 65 million years up until today. We love using microfossils and gastropods and bivalves. So snails and clams, they make excellent index fossils for the Cenozoic.